Hello and welcome back to our mini Rust in Rust series. My name's Andy. This is video 18, I think, and I must confess to being slightly nervous about this video because it's the first one we're doing where I've never done anything like it before, so I'm probably going to do it all wrong. So I hope you'll forgive me when that happens. So we're here in the main method of main function of our mini Rust interpreter that we've been writing, because I think this is how we're going to think about this for a while at least. So the main function returns a result, and otherwise, like, if something doesn't go wrong, it like does what your program says. So the way it works is reads your program into a string, like the whole of it. So, maybe that's a problem, but not for now. And then lexes it into some tokens, which it collects into a vector, which again, maybe we don't want to do that. And then passes it into a collection of syntax trees, syntax trees, a forest of syntax trees, and then evaluates it, which is like do stuff. And in each case, we've got this question mark operator being used. And the first thing I'm going to do, having just had a look at this a second ago, is change the types a bit, and instead of having a question mark there, I'm just going to have the question mark happen immediately, so that the this code gets a lot tidier if we do it that way, and I think it will still work. The problem is it doesn't know what to do. It doesn't know how to collect this. That's interesting. Why can it not figure that out from the types? I guess that's why I wrote it this way, but that just seems surprising. Maybe we'll figure out that actually wasn't something else is going on here. That means that's... Yeah. So the problem is... Okay, the problem is that this collect is doing a lot of work for us, because actually what collect is doing is turning it into a result of vec instead of a vec of result. So I guess we could just do this and make that easier. I'll make it a bit neater, like this. How's that going to work? It needs to know the error type, maybe, or no? I don't understand why that would be a problem here. Cannot satisfy it from iterator. This was going to be the tiny little chunk at the beginning of the video before we did the difficult stuff. Cannot satisfy it from iterator. Let's get the full compiler, shall we? So it's when we're making tokens, we want it to be a result of vec of token. We cannot infer the type of the type parameter b declared on the method collect. So collect... I guess it's just because... okay. It's because I left the question mark here and I shouldn't have. Okay, that's why that last thing went wrong. Okay, so... I guess we could instead do this if we prefer. But it's a real mess. We could just tell it the type here. And then question mark it there. And I think that will be okay now. It just feels like a real mess to do that, which is probably why I did it the other way. But anyway, there's a method to my madness. This line is probably a bit better than it was. Let's do the same here. So the reason I'm interested in this is because we're going to reuse syntax trees twice. So I just want it to be a nice simple vec and not a result of vec when we deal with it. All right. So then We can have our question mark here instead of here, just like before. And then eval, we're already doing what we need. So when we have our syntax trees, we call into iter on it in order to pass an iterator into eval. And soon we're going to want a copy of syntax trees, or at least we're going to want to do some type checking on that syntax trees object without consuming it. So first of all, let's do a little commit of that, because I guess that's a thing. Let's just check it still works. I guess we should run it as well as running the tests. 3 minus 3, what do we do? 3 plus 5 gives us 8. Okay, so that kind of works. That's interesting. I was expecting line by line, but that's not obviously not how the program works at the moment. Okay, so that works. So let's do a commit. This is short circuit errors in main earlier. All right, so now we've done the bit that was going to take me 2 seconds, and now we get on to what does type checking look like. And I wanted to start in the main method just to think about like what it's like in real use, not just in the test environment. And I think what it's going to look like is basically we're going to do some kind of type check. We're still going to pass in a reference to file contents because there might be errors. And we want to like point at the bit of the source code where the error happened. And I think we're going to want to refer to syntax trees like this. And we're going to want to iterate through them, but not into iter, because we still want to have syntax trees available to call it into iter here. And then I want to question mark it. And basically I want to say fail if type checking goes wrong. And that means we need a type check function. I'm going to write my functions here and extract them out later, like I actually did with the lex and the parse functions before. But I'll just have a quick look at how file contents gets passed into eval. Okay, yeah, let's have a function that looks a bit like this. I think it's going to need some of that business where I is an iterator whose item is syntax tree like this. So that shouldn't be called eval, that should be called type check. And if type checking does nothing, this should be, I guess, the item is going to be a reference to a syntax tree when we're type checking, is that right? And this is going to be yeah, oh no, okay, so this is not going to return values, that is wrong. It's going to return absolutely nothing. And it doesn't like this. Okay, we need a lifetime for these syntax trees that we're being passed in. So we'll just make that be a generic parameter of our type check function. Now, what's it complaining about? Oh, we need a result. We need to return. So we do need to return value. And we get result of just nothing. So if it's all fine, we just return a unit type. And I guess that means we need to return OK. And once we've written ourselves an empty type check function, everything should work just as it did before. Now, of course, that would include the main method, because that's the only thing we've actually changed here. And it does indeed. If we ask it to add up 4 and 3, we get out 7. So things are still working. By the way, what happens if we ask it to add up 4.0 and 3? Something bad. All right. Well, I guess we'll get to that. But not right now. So type checking. What does type checking look like? Well, I've been thinking about this and thinking that there's a lot to think about in the way Rust checks types. Because it does type inference, and it figures out like all the possible types that things could be. And I guess the way I'm thinking about it at the moment is it uses the different constraints on that type that come from different places. For example, it looks like an integer in the literal, and then I'm assigning it to, say, an i64 variable. Well, those things are compatible because things that look like integers can be treated as i64. So therefore, the literal itself can be kind of understood as an i64. Something like that. So it uses that kind of reasoning of like distant things affect each other. It looks like I'm returning the number 3, but this function, the return value of this function is string. Those things are not compatible. So it has to pull together information from widely. Now, because of the way function signatures work in Rust, where you always have to be explicit, until we start thinking about generics, which I just have not thought about because it's too hard, it's pretty straightforward, as in it's all within the scope of one function, and outside of a function everything is explicit. So when you call another function, you know the types of that function. Now, of course, when we talk about generics, that's going to get much harder, but we don't need to think about that. So I'm going to start really simple. The thing that we want to the test that we want to pass is that when we try and assign a floating point number into an integer variable, it gives us an error message. So we don't need yet to pull in information from widely dispersed sources. We can just look at one assignment statement and say, does this assignment statement make sense? And we can think later about how to pull together information from different places. And I believe, if I remember right, we actually wrote the test probably in the evaluator, I should think, as our guiding test for type checking. But we now want to move that. Yeah, here we are. Here's our test. But this doesn't live in the evaluator. It lives in our new code that we're writing now. So it's going to briefly be in main, and then soon it's going to go somewhere else. So we're going to have a tests module containing that test. And we're going to, and it's not going to be eval. Oh gosh. Okay. This test is going to look different from how my guiding test thought that it was going to work. It's going to look like this, type check, which is going to be brought in from this module, and it's going to use parse unwrap and stuff, just like what we had before. So I guess we will copy parse unwrap. And we're also going to need to bring in some more stuff to make this work. Oh, and we don't need to do any nexting or anything like that. And so I guess it's just going to need one unwrap error on it because we're returning a result. We want that result to be an error, so it should come out looking like this. And also, by the way, I've been thinking, and I'm not that keen on this error message. So if we can do better than this error message, I'd be interested in doing that. Although it's not too bad, is it? But I kind of would like it to say, I expected the type of X to be I32, but I guess this is okay. Okay, so let me put that on hold and say some of the type error messages in Rust I found really confusing. And if we have the ability to do better than that, at some point in the future, I would like to do that. But I won't say that about this particular one because it actually seems to explain pretty well what the problem is. All right, so bringing stuff in. In order to test our type checker, we need to parse and lex our code. As we may have talked about earlier on, another option would be to provide a syntax tree directly to the type check function, and that would be a kind of more pure test. It would only test the type checking code and not test the parsing and lexing. I don't really buy that kind of that style of testing where you go for the kind of minimum surface area of code that you're running, because it's just obviously so much easier to understand our test if we write it in code like this. And we've got other code that checks the parser and the lexer, so I think it's okay to rely on them here. But that's just me. Other people disagree. And this should... Alright, so it's returning an iterator whose item is a syntax tree. So we actually need it to return, I think, a vec of syntax tree, because we're going to pass in a reference to this. I don't know if we need that plus use anymore. Probably not. So I guess we'll do a collect on this. Like so. Looks good. Oh, we're just unwrapping everything as we go. That's fine. Because we know we can trust this code by the time we get here. That's the theory. All right, so let's do let syntax. Oh no, I guess we could do this all in one still now, because we can just say dot iter on this vec that gets returned. And now we've got the right type of iterator to pass into type check, which is something that has an iterator of type a reference to syntax tree. So if we've got a vec of syntax tree and we call iter on it, we get an iterator over references to those syntax trees because we didn't take ownership of the thing. We need that because later this syntax tree is going to get passed into eval. But anyway, okay. Yeah, so main at the moment is implemented very inefficiently, because we're not actually using the fact that these things are iterated, so we don't need the full vec to even get created. So we can make this main nicer. But of course, I'm now kind of reversing that in the case of the type checker, because I actually want to iterate through the syntax trees twice. First to check the type and then to do the evaluate. Now, at some point, we might want to think about does the evaluator use the information that the type checker has got? So actually, does the type checker provide some kind of annotated syntax tree, maybe, which the evaluator uses? That would be very interesting, wouldn't it? So that's an idea that we should keep in mind. Maybe I'll just add a to-do here. Maybe the type checker returns an annotated syntax tree with types in it that is used by the evaluator. So I don't know if anyone's watching this and you know that is or is not a good idea from what work you've done. I'm very interested to hear. But I'll just plow on, not knowing what earth I'm doing with writing a type checker. So we can still cargo run, everything still works. Oh no, let's cargo run something that actually works, and it does. And hopefully cargo test should now fail, because we just added a test that shouldn't work. But we have still ignored it. Yeah, so that would be why that passed. So now when we run a test, we get some kind of panic because we get back an OK from our type checker, because our type checker does nothing. So far, things are looking sensible. How far are we going to get through this type check in this video? We'll see. So what I think we're going to do is iterate through the syntax trees and find the type of each expression, and then apply some rules for each type of statement that we've got to figure out, like to check that the types make sense. So for each type of expression there is, we'll do something different. We don't have too many types of expression at the moment, so hopefully it should be okay. So let's iterate through the trees. And for each tree, we're going to match on it, maybe itself. Is it an enum? I don't remember what these things are. Yeah. All right, good. We're going to match on them, and they are going to have different types. So a leaf type in our is essentially like a statement which consists of, well, that's a little odd, isn't it? It's it's not even a statement. It is a it's like a part of a statement, which is not like, so it's the kind of thing that we evaluate, like when we passed in 3 plus 4 to our main method. Well, it's not even that, but if we pass in just say 3 to our main method, it would be that. So I'm going to say for now, there's no type checking to do on a leaf. And then I'm going to say an operation is going to have some type checking, but we're not ready to do that yet. By the way, I don't know why my Rust analyzer is putting these odd expressions in. These should be just a to-do, I think, and there's some kind of bug in my version of Rust Analyzer or something. And I guess at the end we should return OK. And I'm already starting to think this might be not working out the way I expected, because maybe when we type check a leaf, we should be returning the type that we found there, or the kind of type constraint, I guess we'll call it, because it may not be a concrete type. And that would mean that something like the assignment statement would be able to recursively call type check on the leaf inside it. Oh no, but it doesn't have a leaf inside it. It has an expression inside it, which is of type. Oh no, yeah, which is of type syntax tree. So it has a leaf inside it. Yeah, so it might be interesting to call type check on a leaf, get back its type, and then use that in the code that evaluates. I think that's a good idea. So that, well, but I guess we want to call type check on just not, we don't want to, type check itself probably at some point might return some kind of iterator of types or syntax tree annotated with types or something. We want to type check a single thing. So I think what we want to do is call like type check tree on tree, like so, and then this stuff will happen inside there. So let's see how this goes. And it's going to take in a syntax, I guess a reference to a syntax tree. Is that what tree is? Yep. It's going to take in a reference to a syntax tree. And it's going to return a MET result of I guess the type, let's say. MET results. And this, so the result here is going to have some kind of thing in it, which is going to be, I think we're going to call it a type constraint. And then somehow we've got to find a way of like asking our type constraints compatible with each other. So this is all very exciting. So is this coming together, or is this going to turn out to not work at all? We'll find out soon enough. So there's going to be a thing called a type constraint, which we're going to return from our type checker, and I guess we're going to, each of these is just going to call out into something else called type check leaf. Maybe these should just be called, like when we move this into its own module, maybe this should be called just leaf and tree. But at least for now we won't do that. So what is leaf token? It's a reference to a leaf token. Fine. And yeah, I think that's fine. We'll just call it. And if we have an operation, then it'll be something similar. I need a comma, don't we? Well, let's leave the others as to-dos for now, and let's just try. So let's have a to-do here as well. And let's just try and implement type check leaf, shall we? So can you make this function for me? Oh, not bad, not bad. Oh, well, close, but no cigar. We want it's done the right thing, but not written it the way we want to write it. So it's going to be something like this. So what's the type constraint of a leaf token. So what does leaf token has a kind? So that's probably going to be how we figure this out, isn't it? So let's write a test for this function. We may only get as far as testing this function, this video, we'll see. So this should be a type of function, type of int literal is int, right? So let's just pause for a second to talk about this. So when you have in Rust code, when you have a literal that looks like an int, as it's a load of numbers, maybe with underscores, although by the way, we haven't implemented that yet, but that the type of that will default to be an i32 if you don't say what it is, a 32-bit integer. But the type of that literal is not actually i32 itself, because if you do let x colon i64 equal that integer literal, it just immediately treats that. It's the kind of coercion that Rust does actually do, kind of, which is that it treats that literal as an i64 literal immediately right there. And in a compiler, that's super important, right? That it figures that out up front before it does any evaluation, because it's actually going to allocate the correct amount of memory for it based on that type checking. In doing type checking in a interpreter like we are feels odd, because maybe that type information just gets thrown away before you evaluate, but I'm hoping we're going to figure out that it doesn't, and it all fits into a nice pipeline like we've been doing all the rest, but we'll see. Okay, so our test is going to look like when we type check a leaf, where a leaf is a leaf token, then the answer we get back, so this is going to be a leaf token that's some kind of integer. The answer we get back is going to be a type constraint int. I think we'll call it for now, we'll see. So what type of leaf token do we have? Oh, I guess the span we don't care too much about. But let's imagine it's an int of like made up of 3 characters, so maybe it goes from 0 to 3. I think that's what spans look like. We'll find out soon if I'm wrong. And the leaf token kind of int, and I think that holds on to a string, which is the actual token itself. So let's make it be 818 for some reason. That should be a string, not a str. Let's bring that in. That's not how you spell constraint. So let's bring that in as well. No, not that. And I guess we want to... in my tests, I tend to want to use super : star. I think we'll do that here, which means I don't need to bring in type check or type check leaf. So what is it moaning about? Should be a reference to a leaf token. Oh, and I misspelled type constraint up here as well. So that would explain that. So now the remaining problems we have are that these are all unused, which is okay for now. No, it should be, I guess it should be, I mean, for now we just ignore them, shall we? Like so. And again, I've misspelled type constraint here too. So we should now have, yeah, our remaining problem is that there is no enum value in the type constraint called int. So let's add one. So this is looking weirdly similar. The leaf types, the type constraints are looking similar to the leaf token kinds, but I think that's okay because they don't contain. I don't think a type constraint will contain any information about actually what type, like what the actual value is. I don't think, although we'll figure that out. But also there's going to be other types of type constraint. There's going to be specific things like I32 in here, as well as these general things like int. So I think it's going to work out that these are actually different. All right, it's moaning about how type constraint can't be compared against things and can't be printed in debug. So we'll do that. Debug and partial eq should do it. It's complaining about it not being used. And oh yeah, it's a result, so we need to unwrap it because the type checking here should not fail. So let's just make that clear. Type checking and int should not fail. In fact, it's really type checking a leaf. That would be more useful information for the reader later, wouldn't it? No kind of type checking on a leaf should fail. You just tell me what type it is. Okay, so maybe type check is the wrong word. Maybe it should be, type eval. Anyway, we'll see. All right, so now we've got two tests, and this test is far too complicated for us to understand. So we'll go back to ignoring it, and we'll see whether our new test fails in the way we expect. Yeah, it hits a to-do, and also we hit some warnings. What warnings have we got, and should we get rid of them yet? Well, that's unused, it's fair enough. And then this variant is never constructed. I guess that's complaining about. Yeah, we're about to construct it, so it's fine. All right, so I've made this type constraint struct in the middle of, in the middle of all my other stuff, which is probably wrong. So, well, let's just put it immediately before main, shall we? Okay. Maybe we'll add a dot comment. I've been getting into dot comments. I should be writing more of them, shouldn't I? This is what I guess it's kind of what we know about the type of some construct in our program. Could be fully specific, e.g. this is definitely an I32, or more general, e.g. this looks like an int. And if we had nightly Rust, we could format this comment, wrap this comment in the way I want. Anyway, okay. So type check tree is what we're unit testing right now. Well, type check leaf rather is what we're unit testing now, and type check leaf currently just says to do. So what if we return? Oh, well, this is too easy. What if we just return type constraint int? Then our tests are going to pass. So we haven't written enough tests, is what that's telling us. So let's check what the type of a float literal should be. Type of float literal is float. Float. So this is going to be 12.82. And oh gosh, we're not passing in. We may need to pass in the the reference to, given we got these spans here, we may need to pass in a reference to the file contents so that we can provide decent error messages. So keep your eye out for that. So that should return a float, which doesn't exist. So let's make that exist. And I guess float comes before int in the alphabet. And run our tests, and one of those will fail because it's still returning int for everything. So now that forces us to write a better implementation of type check leaf. So we're going to match on, I think this is really simple. We're going to match on a leaf tokens kind like this. Here is where I'm quite glad we haven't done too much. We haven't implemented too much before we get into this stuff, because how easy would it be for me to write this code if we had hundreds of these and I had to somehow handle all the cases. Alright, so if it's an int, we return int. If it's a float, constraint : float type constraint. And if it's a symbol, we don't know what to do yet. Let's bring this in. Oh, and this should always be, I guess we can wrap this in an OK. Whenever we type check a leaf, it should never fail. So maybe we shouldn't even return a result here, but it feels neat because these others are definitely going to return results. It kind of feels neat to do it here. So we'll see whether we like that or not later. So notice type checking a leaf node that is a symbol. So like an expression like X, which has the type of whatever the type of X is. That's going to require multiple statements interacting with each other, which is way too difficult for us. So we're definitely not doing that yet. We're just going to do this. And it's going to be whatever the type. You're going to look up this symbol somewhere, the symbol name somewhere, and figure out what type we think that has, and then this will kind of inherit that type for this expression. I think that's going to work, but I really have not thought this through, so we'll see. All right, so I think our test is going to pass. Yes. Type of float literal is float. I can see that in there, so it's all working. So we have a little function working, and that means I think we're now ready to try and type check an assignment. So I guess we could have a test for that. But this is kind of our test for it already. So let's just plow on and let that test be our test. And we'll see whether we're happy with that later. So type check assignment is going to be a function. And we're going to want those variables that we glossed over here. Like so. And how many of these do we need? Well, probably all of them at some point. But yeah, we're not doing. Let's think. So at the moment, maybe we just need the type, because currently we're not. Well, maybe we never. Right. Well, let's pass in the type and see how far we get. And at some time, surely we're going to need the others as well. Can we do this to ignore them? Looks like it's allowing us to do that. Let's make a function called type check assignment. Guess we'll put it after type check leaf because it feels right. And, this has all gone terribly wrong, hasn't it? Anyway, this thing is called type underscore, and it is an option of reference to symbol token, and it's going to return a get result of type constraint, like so. And we'll have that, and we've got a reference to an option of a symbol token like this. Not sure why it generated. Did it generate the wrong thing, or did I mess it up? I don't know. All right, so our test is now failing. The guiding test we're using is now failing because we've hit that to do in there. So we're all good. We're getting there. So when we're type checking an assignment, if there is a type in there, then I think the type of it's very clear what the type of the right hand side should be. And if we don't have a type, I think there's not much we can do here. We should just return the type of the right hand side. Yeah, I think that's it. So let's get hold of the type of the right hand side. Let right hand side type equal type check tree on. Oh, now we did. Okay, so we immediately need part of this, which is we need expression. So I'll pass that in. And a type of expression is a reference to a box of syntax tree. Expression box of syntax tree. Comma. So we're going to type check tree on that syntax tree. So if we just dereference expression, is it going to let us do that? Looks like it. So now we've got the right hand side type, and there's two things. Either the type of, the type of an assignment is always like the unit type. So we're going to need type constraint unit, and I guess we should test that somehow. So this is actually always, you're always going to return a unit type. So let me just talk about that. So this expression here, this statement here is a statement. Well, if we include the semicolon, it's a statement, and without the semicolon, it is an assignment. And we could call that an assignment expression, but it's a very odd type of expression because in Rust, an assignment always returns the unit type, as in bracket. So no matter what type checking we do on the contents of the assignment statement, we're always going to return unit, I think. And we'll see whether I'm right about that as we keep going, I think. Which means unit is definitely a type. So, by the way, maybe there should be some kind of subtype here, which is like, these are like vague type constraints, and these are like exact. So maybe it should be like exact with some kind of exact type constraint. Colon unit, and there could be an I32 and other things in there. Maybe it should be something like that, but we won't do that yet. We'll keep things simple until we need them complicated. So so far there's no test for this, so I just need to put in a to-do so I don't forget. Test this, return value. We've got to remember to do that. But what we're here for is to check that the types of this assignment statement make sense. Now, if we haven't expressed the type with a colon I32 or whatever in our assignment statement, then this will be none, and there's nothing for us to check. But I am thinking we do want some information to leak out of here. So somewhere there's going to be some kind of record of what are the types of all the variables in the current environment. And we want this assignment statement to leak out this right-hand side type into that environment to say when we made it, the right hand side of its assignment was this, and therefore that affects its type in other places. So at some point we're going to be passing in some kind of modifiable environment into here, maybe. So that's all very interesting, and maybe this whole structure doesn't make sense, but so far it does. So we're going to stick with it, and we'll gradually grow our code as we understand it. So in the case where you have specified a type, so you have done colon I32 or similar, then type checking an assignment means checking that the type matches the right hand side. So what is type? Type is at the moment it's a symbol token, an option of a symbol token, but we've said it's not an option, so it's a reference to a symbol token. So we need to kind of resolve that thing into another type constraint. So this should be something like, I guess maybe we could do type constraint from type, maybe. So the left-hand side type is going to be that, and maybe that will go wrong. And then we just need to check if left-hand side, I guess it's if not types compatible. Or we could just, should it be a method or not? That's what I'm having over. So should the left-hand side be compatible with? But it's not that, it's actually combine. So we actually want to combine the types. Combine types. Or maybe we do left-hand side dot combine with right-hand side, something like that. And we're not actually, like, I think this will eventually it will return some kind of type that we use somewhere else. But right now, let's just call this, I've started calling it right-hand side, let's just call it that. Is that confusing? We're in the type checking code. I think the fact that this is a type is kind of okay. So what I'm trying to express here is find out the type that's expressed by this symbol. Could go wrong because maybe this symbol is like not a type, which in itself might mean that symbol was the wrong thing to use here. And then basically, if we've got, say, int and I32, those should combine together to I32 because int is less specific and I32 is fully specific, but they're compatible. But if they're not compatible, so left-hand side is float and right-hand side is I32 or something like that, then this should return an error. That's what I'm getting at here. So let's figure out how we can do this type constraint from thing. So near our type constraint enum, we want to do some kind of impl from reference to a symbol token for type constraint. I don't know whether from is the right way to do this, but we'll see how far we get with it. If generally my rule of thumb is try and use standard things like from, and then when it doesn't work, give up. But that might not be, I don't know whether, it feels like it is a conversion. That kind of makes sense for me, so I'm okay with it. All right, so how do we do this? I guess, what does value have inside it? It has the actual symbol, so we can match on the symbol. No, we can't. We just need to examine the symbol. So I don't know, let symbol equal value dot symbol, and then if symbol. So hang on, hold it. Why is there no test for this? So before I do any more, let's test this. So okay, let's make it compile. So let's write a test that says I guess it's constructing, can construct a type from a symbol. Or is it actually, it's more like, well, I don't know. That might be way too general. We might need loads of tests for that. But for now, we only need to know that when we try and make a type constraint from a symbol token, we should get back type constraint I32, where the symbol is, this is going to be some kind of span, which is, and again, just coincidentally, our thing has 3 characters, but it should be a string. So basically what this is saying is when you come across a symbol, which is I32 in a type position, so we're trying to make a type constraint from it, the type constraint it should return is type constraint I32, which doesn't exist yet. But it's going to go here. And yeah, I'm starting to like the idea. Let's have a little to do that. To do, maybe all exact types should live inside a sub-enum. Let's just say that I should remember what that means. So, this should be, I guess, try from, because, but you need to be able to, I don't understand that. We'll look at that in a second. We need to be able to fail in our conversion. So we shouldn't be implementing from, we should be implementing try from, which means our method will be called try from. It's going to look like this. It's not going to have one of these. And now we get to specify the error, which is going to be miet error, I hope, if that's allowed. And do we compile? No. Because we didn't implement combine with. So type constraint is going to need a combine with method, which should return, it's going to take in, is it going to take in self and right hand side and return, is it going to destroy itself? Like, that kind of is an attractive idea. It destroys itself and the other one and just returns one, which is the combination of those two. Let's see whether that makes sense or not. If that becomes annoying, it can take references and it won't do any harm at all. It's just feels good. Okay, we failed because combined with should be returning a result. Before that code we wrote down the bottom with a question mark is going to make sense. And we've got one other error. Type constraint from, it should be try from. And that should be, we should unwrap it by saying, should be able to make a type from I32. I guess that is. I mean, maybe we could unwrap there and it would be okay. Alright, so when we run our tests, 2 of them are going to fail. The guiding test is going to fail, and the little one that we've written is going to fail because we haven't actually implemented try from. But for now, we can implement enough of try from by just saying if the symbol is I32, we know what to do. Otherwise, some kind of error. So, I guess we're going to do some kind of to-do test this. If it's an I32, well then it's type constraint I32. I guess we're going to wrap we're going to wrap this whole thing in OK. For now, we'll put the OK here because it's going to get really ugly, but we might well want to wrap this whole if in an OK. Excuse me. So, okay, so our little test is passing. We are now able to make an I32 type constraint from this symbol I32. And now we're failing at line 94 because there's other stuff we haven't implemented yet. Okay, our first problem is that we're not actually implementing type checking on a statement. But I think we can, this should be, I guess this is expression. It's the expression inside the statement, the expression that the statement consists of. So I think we should just recursively call ourselves on whatever the expression is. So this should be type check tree, I think. Is this going to work? I think that works. Okay. So that was our first to do, but then our next to do is on line 57. We haven't done combining together left hand side and right hand side yet. So we need some tests for this too. This is starting to look like it might even be multiple files, this type checker. I'm ending up with tests that all fit into different categories. So combining, I guess this goes after. It's less kind of basic than just making types out of symbols. Combining, let's have combining equal types returns the same. So we could do some kind of assert eq of type constraint int combined with type constraint int is going to equal type constraint int, right? Simple as that. If you combine an int with an int, you get back an int. And this needs unwrapping. Shouldn't fail. I guess we can say shouldn't fail. Combining with same type should not fail. And while we're here, as well as ints, let's do a few more. So we'll do floats and I32s. I don't think we're going to list all the types here. I think we just want a representative type, representative sample. So ints and floats are two non-specific types. I32 is a specific type. We do have one other specific type, so why not include that as well? So we've got a couple of examples of each. We'll just include unit as well, because that's another specific type. And yes, unit is a type, and it is specific. There's only one instance of unit, I think, depending how you think about it, but that's separate. All right, so combining equal types returns the same fails because we haven't implemented combine with. So let's implement it with, first off, just saying if the two are the same, then return self, or whichever, either one. I guess it should be okay. Like so. We need some kind of else, don't we, for going wrong. And we should have another test here to do test this. So we've got a load of to-dos we're going to fill in after this. Now, how far are we getting? Okay, well, our new little test passes, but we're already immediately hitting our to-do in the case where they're different. So let's write a test for our specific case, which is combining let's just do specific. Combining an int literal with i32 gives i32. Simple as that. So we've got an int combining with an i32. The answer should be i32. And while we're here, the other thing we should definitely cover is the opposite order. And this is why I was umming and ahhing about whether it should be a method, because it's fundamentally commutative. Either way, you should get the same answer, right? If you combine two type constraints together, you should get the intersection of the set of those types. So this should be combining. I mean, really, this is just like, this should work. So I kind of want to just unwrap this. I think unwrapping in tests is okay. Sometimes, not always. So that should fail. It does. So let's make this case work. And let's be really dumb about it and make it cleverer when we know more. So if self is int, left is int, no, self is int, that should be called. And right hand side is i32. Then we're going to return type constraint i32, and let's run our test and check that it does actually check. That should be okay, obviously. Let's run our test and check that it does check both sides. Yeah, it still fails because we need an OR. We don't technically need brackets here. This is horrible, isn't it? Type constraint i32 and right hand side equals, we can maybe make this nicer with some kind of matching, which we'll do in a minute. Now our test should pass, leaving only the one guiding test failing. So how can we make this better? We could do some kind of matching, couldn't we? We could do an else and then match on the pair of self and right hand side, and just say that bracket should be there, and just say if it's I mean, maybe part of the problem here is that I'm not importing things the way I should. I think we can do this and then just say i32, and if I import these in the right way, this should be okay. And otherwise, I guess we've got to do something else, which is going to be to do other types. Now, I'm feeling like there must be a way of representing the fact that this is the same either way round. If we could somehow sort self and right-hand side, this is so not working. If we could somehow sort self and right-hand side so that we only needed to say one of these two orders, that would be better, wouldn't it? All right, so obviously there's no further else. That's the main thing that's going wrong there. Now, can I somehow import, but only in here, the names? That's what I want to do, just to make this read easier. Yeah, that's nice. That's what I want. Okay, does that still pass? It does. I think. No, it doesn't. I was expecting our guiding test to hit this case of int and i32, because our guiding test says if your type is i32. Oh no, of course it doesn't work. It doesn't work because our guiding test does not is wrong, and it's an error case that we need to somehow check. So I feel like we need another guiding test, which is assigning the right type is not an error, right? And I think we've made that the right type explicitly is not an error. I think we've just made that test pass when it was previously failing, which is a little unsatisfactory that we didn't see. So this should just be this, we can just expect on this, I think. Should not fail. Should be okay. That to do, we've actually done. We've moved it to the type checker code, so that's good. All right, so yeah, assigning the right type explicitly is not an error. Now passes. Now I want to make sure that it would have failed until a second ago when I wrote that code. So let's go back and make this code wrong and check that it fails. So if I just get rid of that line, it fails. Yep. All right. So we've got like some of the happy path working, and to make our guiding test pass, I think we want the unhappy path to say you can't do this with an int and an i64. No, sorry, a float and an i32, and construct a nice error message for that. So I think probably we're going to leave this video here. Yeah, we're going to leave this video here. We've got a decent way with some kind of idea of what type checking is going to look like, and we'll carry on next time. So I hope you enjoyed. See you then.